goal for today is the rational functions. I do want to remind you what's coming up on Friday. Your test, that's exactly right. And so you want to make sure that you have gotten all of your definitions and theorems learned at that time, and that you know how to use your derivative rules to find derivatives, and that you know how to use the limit definition to find derivatives. And there it is. I have noticed that the study guide is now much more up to date than it used to be. The study guide elves have been working hard. And I have indicated which of those derivative rules you need to be able to prove. The power rule is not among those.
Thank you.
You're welcome. All right. Anything else I need to say? Delina, did you have a question? Does the test include everything you've learned in the past? The test is going to include everything that we've done in Chapter 3 so far, which is derivatives. So in particular, you need to know the definition and the alternate definition of the derivative. You need to know that it represents, you need to know that dy dx represents several things at once. It represents an instantaneous rate of change. It represents the slope of the tangent line. It represents the slope of the curve. This is the discussion that Tifa and I had on Emoto. And in particular, if the tangent line is horizontal, then what does that tell you about the slope at that point? The slope is equal to 0. That's right. And please notice that this is not the same thing as the derivative when x is equal to 0. But it is the point where the derivative itself is equal to 0. What's the other way that I can spell the derivative besides dy dx? Yes, and the reason we have two different spellings is that we had two different people who discovered calculus, and as a result, their 30-year battle over priority led ultimately to two different, really three different, but I'm not sharing Newton's notation with you.
What about d over dx?
Good. So this is an important thing, and Harry, this is important for you. I noticed on one of your things. Please notice that dy dx is a rate of change. The derivative operator, which is spelled d dx of, not dy dx of, is an operator that takes a function and gives you its derivative. So if I take the derivative operator d dx of y, then what I get is dy dx. d dx of y is the same as dy dx. Yes?
Question over horizontal tangent.
Yes.
Just to make sure. If you simplify that down for f of x, it should give you a value of x.
Yes.
Which you then plug back into f of x to a point.
Yes.
That's one.
Yep, that's right. So for example, if I need to find the horizontal tangent of f of x equals x cubed plus 2x or something like this. Can't do that. How about x cubed minus 2x? There we go. I need to find the horizontal tangent or tangents here. Then I would first find that rate of change, f prime of x, and I can use any tool at my disposal to find that rate of change. What's the easiest way to do it for this particular function? Polynomials, so I can use my derivative rules, right? I don't want to use a limit definition here if I don't have to. And so I take the derivative, I get 3x squared minus 2, and because my tangent line is horizontal, I'm going to set that equal to 0. And that's going to give me now two solutions which are plus or minus root 2/3. And usually I just ask you to find the x values here, and I don't ask you for the y values usually. On the one horizontal tangent exercise, I ask you to sketch them, so you have to find the y values. But usually I just want you to find the x values. Does that make sense? I'll take that as a yes. Okay. Good. Since I have not seen any questions out on Edmodo about the homework, I assume that the homework is going fine for you guys. If you are not doing it, then you're doing this class wrong. Just to let you know.
Will and I were talking about number 51. I got one answer, he got something else, and so we're a little...
What the back of the book says?
390, which is what I got.
Okay.
And so...
I originally got something number, then I went over, reread the whole section, read the section, and I got 390.
All right, let's take a quick look at that.
Okay.
An apple farmer currently has 156 trees. Yielding
12 bushels of apples per tree. I mean, just read it. He is expanding his farm at a rate of 13 trees per year. While improved husbandry is improving his annual yield by 1.5 bushels per tree. What is the current, in parentheses, instantaneous rate of increase of his total annual production of apples?
Of his total production?
Yes.
Okay. I want all of you, including your NKG, to pay close attention to what's going on with this question. This question is not a hard or difficult calculus question. It is a hard translation question.
Yes.
All that needs to happen is to properly translate it from English into math. And so to do that, we're going to look for certain phrases that we know the meaning of. And we're going to start with the verb. What is? We want to know what is something, and that something we're trying to find is the instantaneous rate of increase of the total production of apples. This is what we need to find. And the reason that we zoom in on this is that the phrase instantaneous rate of increase is a synonym for what mathematical quantity that we've talked about. Bingo, it's a derivative. That's exactly right. And now we need to establish the derivative of what with respect to what? D what over D what? That's our question. So we go and we look at the rest of the language. It's the rate of increase of the total production of apples. So we have the answer to our first question. It is D production over D something. Let's let our units be our guide. What do you see here that might tell us is that variable in the bottom? Do you see any other rates given in the problem?
1.5.
1.5 bushels per tree?
Yes.
And
13 trees.
13 trees per year, right? So we've got a couple of different rates going on here, right? Now the next question is, what is this production increasing with respect to? Is it increasing with respect to trees or time? Yeah,
Time.
because,
Because if you multiply 13 trees per year by 1.5 bushels per tree, you get the unit bushels per year.
yeah, so that makes sense to me. So what we're going to be doing is we're going to then let P, or some other suitable variable, be the production. In bushels per year. And we're going to be looking then for dP dt, which is the instantaneous rate of change of that production. This is the first time, but not the last time, that we are going to translate a derivative as an instantaneous rate of change. Now we have to come back and we have to ask, what is my equation for P? Because I will not be able to find a dP dt unless I know what P is in terms of time. So what we need is a basic formula that is going to come from common sense or algebra 1 or something like that. Nothing really hard. Let me go back to this guy right here. If I have 156 trees yielding 12 bushels per tree, and I asked you how many total bushels do I get, how would you find that? That would be my total production. How would I get that? Yeah, you just multiply. That's exactly right. So we would say that my production would be 156 times 12 at that moment in time. Does everybody agree with that? But now my 156 is changing because I'm adding on trees per year. And my 12 is also changing because I'm getting better at harvesting my trees. So instead of 156 and 12, I'm going to need to represent them with variables that can change. What is a suitable variable for the number of trees?
T.
And let's make it capital T so it's not time. And what is a suitable variable for the 12 bushels per tree?
B.
B for bushels. That works for me. So we now have a formula, production equals trees times bushels per tree, that gives me the production for any number of trees for any number of bushels. Does this make sense to everybody? This is our mathematical model for the production. Why do I call it a model? Well, because it isn't exactly reality. I don't get exactly 150, I don't get exactly 12 bushels per tree, right? It's not like every tree is exactly identical and I just go and I do exactly the same thing. I'm going to get a little bit more here, a little bit less there, and it all averages out to 12 bushels per tree. So this is actually a statistical model, really, for the whole thing. But it's nice and simple, and that's what we like about it. So this is really the first time that we've had to create a model with our bare hands, except maybe back when we did the linear functions. We're going to be doing a lot of this modeling. So if you have any questions about how we got this moment is the time to ask. No questions? Yes.
Is instantaneous rate of increase where? At what time? At what year?
Ah, great. We don't know, so we're going to assume that it's at the time when this information is true. So you make a really good point. Please notice that that time never shows up in the equation right here. And that's okay. We'll handle that in just a moment. Yeah. So this is sort of like year 0 or something. And we just don't know how that's going to be affected by time. Once I've got the model is the point at which my calculus kicks in and everything becomes easy. This was the hard part, reasoning through to our model. So I want to come back and make sure we're all clear on this. The way I constructed this model was I took the numbers that were given and I said to myself, how do I figure out production from these numbers? And that was easy. And then I represented each of those numbers as instead a variable that is going to change with time. So you really start with the numbers to help you reason through it, and then you just do it as variables. All right, now that I've got that, I'm looking for dp/dt, and so I'm going to write dp/dt as the derivative operator, ddt of what t is, which is trees times bushels, just like that. So this is the appropriate calculus way to write dp/dt as the derivative operator applied to what t is. And now my calculus kicks in. I recognize I have a product, therefore product rule. And I apply the product rule, giving me t times the derivative of b plus b times the derivative of t. And when I take the derivative with respect to time of b, I get dv dt. And when I take the derivative of t, capital T, with respect to time, I get dt dt. Just like that. Now it's just a matter of plugging in those quantities. I need to go hunting through the problem to find them. What is the value of t, number of trees, at this time? Go back to the question. What is the value of the number of trees at this time? It is how many? 156. That's right. The number of trees is 156. And what is the 12 bushels represent at this time? What quantity does it represent? B. Yeah. That's why we chose B. B was for bushels. And expanding at a rate of 13 trees per year. What quantity is that?
13 trees.
It sounds like a slope, which is another word for a derivative, which is a rate of change. That's right. This is the derivative of the number of trees with respect to time. And if you're ever lost on that thought, let your units be your guide there. Trees per year. This one's a little bit trickier. This annual yield is increasing by 1.5 bushels per tree, but really what they mean is 1.5 bushels per tree per year. That word annual means per year. That was a little tricky of them. So this is really the rate at which B is expanding. You might think because of these units it would be dB, B capital T, but actually the bushels per tree was packed into B, just like that. So I don't like the way they worded that. They made it more obscure than it needed to be. So we have all the quantities we need, and now it's just a matter of plugging them in. That gets us T times dB dt, which is 156 times 1.5, plus the quantity B, which is 12, times dt dt, which was equal to 13 from the problem. And simplify all this, and you're going to get something that's around 300 and something.
You get exactly 300. I think.
Yep. Which means that your business is doing great. This is how quickly your production is increasing. So if you can sell your apples at, well, I don't know, what do apples go for? It's going to be something like $10 a bushel. And you're increasing your revenue by about $4,000 per year.
In 100 years, your grandchildren will be making a lot of money.
Exactly right. That's exactly right. Okay, questions about that? All right. Well, we have a lot to do because we have a quotient rule to learn, a song to sing, and the quotient rule to prove. So let's do that.
Let's do it.
This quotient rule is going to be the most detailed derivative rule we're going to learn all year. But we'll have a song to help us remember it. And we'll have a couple of, under many circumstances, we can use algebra first to avoid it. So there it is.
It's not the reverse of the product rule.
It shows some similarities to the product rule. But to get there, I would need to be able to take the derivative of 1 over g, and I don't have that yet.
May I know water?
Okay. Okay. What I aim to show you is that the derivative of f over g is g times f prime minus f times g prime. So there's my similarity to the product rule. But divided by g squared. Divided by g squared. I'm going to show you how to use it first. Then I'm going to come back and I think we'll do a song. And then if we have time, we'll do the proof. And if not, I'll prove it tomorrow. Okay.
Why is it in the box? Is that just like a second parenthesis?
Yes, it's just brackets. So, It's not a box, it's just brackets. So for example, if I need the derivative of maybe x plus 2 over x plus 1, then I would identify the top function is f, the bottom function is g. And then I would use the form g of x times the derivative of f of x. Yes, I know you can do that derivative in your head. What is it? 1. But at this point, I want you writing the form first so that you remember it, right? And then in a week or so, I'll release you to do quick rules. Less the top function f times the derivative of the bottom. And all of that divided by the denominator squared. And that's my setup. The rest of it is fairly easy because the derivative of x plus 2 is 1, as we said, minus the derivative of x plus 1 is, the derivative of x plus 1 is 1. All of that divided by x plus 1 squared. Yeah, we'll simplify it in just a minute. But before we do, I want to point out some mistakes that newbies make so that you won't be that newbie. First thing is, please notice the order matters because of the subtraction. You have to do bottom d top minus top d bottom and not the other way. Right. Actually, we're going to, in song, we're going to call this low and high functions. The high is the one on top, the low is the one on bottom. So this is low d high, less high d low. Does that make sense? Yeah. All right. The second thing that I want you to observe is these parentheses right here are calculus students' favorite ones to forget. Please do not forget them. You are subtracting the entire f times the derivative of the g. And if you leave off these parentheses, then that subtraction will not happen properly, and you'll end up with some sign errors. So watch these parentheses closely, because you're subtracting all of that. Does that make sense? Same thing here. You're multiplying all of g times that. And the last word of caution is, a lot of newbie calculus students will see a partial factor of x plus 1 and the factor of x plus 1 squared, and they'll want to cancel that. X plus 1 is a factor of this term, but it is not a common factor of the whole thing. And therefore, since it is not a factor of the entire numerator, I cannot cancel it, because cancellation, after all, is really division, right? And so I need to be able to divide factors. If I could do that, then I would just do it right there and make my quotient rule simpler to begin with. But I can't. So those three cautions apply. Don't forget these parentheses. Remember the order. Low D high, let's high D low. And avoid the temptation to cancel a partial factor right here. Now, how does this actually simplify? Well, it's really kind of simple. It's x plus 1 minus x plus 2, and that's negative 1. So my derivative, when I actually get to it, is fairly straightforward.
Okay.
You just go extra right now.
You like skipped it. Okay.
Yeah.
I get it.
Did some algebra that I figured we can do. How are we doing so far? Good. I'd like for you to try one. Go. Use that quotient. Got it? MS, what you got? Okay. So we have x times uh-huh. Well, okay, but over x squared. Good. All right. Now, what is the derivative of 1? 0. 0, because it's a constant. It doesn't change. So this guy goes to 0. And what is the derivative of x? 1. And so that gives me negative 1 over x squared. Just like that. Were you all able to get that successfully? Good. Good. Very good. How about a slightly more complicated one? All right, challenging.
Thanks, so.
Go. Okay, what you got?
I just say all the steps?
Yes, please.
Okay. Then it would be x times the derivative of x, root x plus x,
Uh-huh.
minus root x plus x, times the derivative of x over x squared.
That's good. You probably have it right, but I've got something wrong on my work. Who can tell me what I have wrong here?
Oh, the parentheses, yeah.
Yeah, missing the parentheses.
That's right.
Excellent. No pun intended. Yes. Okay, keep going from here, Will.
Got the x and the that's,
What's that?
I've got the plus x and that so carry on.
Okay.
Will said he.
Carry on from here.
X 1 over 2x 1 over 2 radical x plus 1 minus radical x plus x times 1.
Again, I have something wrong with my work. What is it? What am I missing?
Brackets.
Parentheses.
Parentheses around what?
Around 1 over 2x plus 1.
Yes. This is the derivative here, and all of it is multiplied by x. So I need to make sure that I group that appropriately. At this point, I have computed the derivative. There are no more derivatives left to take. So if I do not need to simplify it, I will stop here. And I strongly encourage you to do that if you do not need to simplify it. If you do need a simplified answer, if your inner nerd feels so compelled, then we could actually do that, and it is often enlightening to do so. I'm going to do that in this case. When I do, I get x over 2 root x. What is x divided by root x? It is root x. That's exactly right. So I have 1/2 root x from this first term.
Wait, say that again?
Subtract exponents.
Oh,
Or another way of putting it is root x times root x is x. So x over root x is root x.
Could you just leave it as like x over 2 root x?
You could, but I'm simplifying it because I said I would. Now, in the subtraction here, we have minus root x minus x, and all that divided by x squared. So now we see the benefit of it. Boom, done. And 1/2 root x minus root x is negative 1/2 root x, and all of that over x squared. And we can do the same thing with the subtracting of the exponents. What is 1/2 minus 2? 3/2, that's right. So that when the dust finally settles, we end up with something much simpler than we had before, which is very satisfying. So I was thinking, tell me your thoughts. Where are you? Here to here?
correct. Answer zero. I don't know that.
Ah, yes. So again, we subtract exponents. We have on the top x to the 1/2, on the bottom x to the 2. 1/2 minus 2 is negative 3/2. You're welcome. Anybody else? Questions on this? Okay. I will prove quotient rule for you tomorrow, but you don't need, the proof does not give a lot of additional insight. And so it's not a proof that I'm going to require you to know for your test. Unlike the proof of the product rule, which is helpful. So instead, we're going to do a song to help us remember it. We're going to call the top function the high function. And we're going to call the bottom function the low function. And so the lyrics to the song are basically the actual quotient rule itself. I'll sing it through, and you see if you can pick out the quotient rule from the lyrics. It's actually being recorded. Quotient rule you wish to know, it's low D high, less high D low. Draw a line and down below, denominator squared root. All right, so did you catch it? Low D high, less high D low. Draw a line and down below, denominator squared will go. Now, the trick is, this is for you to remember. So if you're going to remember it, you got to sing it. I'll sing it one more time, and then all of you are going to sing it. Ready? If the quotient rule you wish to know is low D high, less high D low, draw a line and down below, denominator squared will go. All right, so we're going to sing it through a couple of times here. I understand the first time you're going to be a little hesitant. But give it your best shot, because the more you try, the more you'll remember it. And then all of you will be able to sing it through quietly to yourself on the test and get the quotient rule correct.
Are you gonna pick it up for us or you just give it?
If the quotient rule you wish to know is low D high, less high D low, draw the line and down below, denominator squared will go. That's pretty good. You guys do better than my classes usually do. I usually have to fuss at them a little bit, like early Guthrie fusses. But if I'm going to be a proper math cult leader, then you're going to have to sing louder than this. So let's sing it so Miss Prentice can hear us. Hi, Miss Prentice. Ready? If the quotient rule you wish to know is low D high, less high D low, draw the line and down below, denominator squared will go. That's great. Now for the country version.